Alright, so welcome back everyone, and this is part 3 of this first segment of network attack and defense. In this part we'll look at DNS and the border gateway protocol, things like that, and then try to also look at a couple of attacks. So DNS is domain name service, and there is a global hierarchy of machines that serve out IP addresses for a name. Like for example, if you want to find out the IP address for www.uwrf.edu, this is where you end up going. So if you have never visited www.uwrf.edu through your browser, you type it in. The first thing the browser does is it will need to find out the IP address for that what's called fully qualified domain name. And so there are 13 top level servers in the world, and these are in various locations. Plus there are DNS servers at internet service providers, or even your organization you're probably likely to have. Like for example, in UWRF there are DNS servers at the LAN level and one main one for the entire organization. And if you're at home, chances are you're using an ISP or maybe using a mobile network connection. It'll be your ISP or your telephone service provider that has a DNS server. So they're everywhere. They're sort of invisible. Most of the time you don't have to bother with even doing anything with DNS yourself. It's all the software that takes care of contacting things like DNS servers at various levels. So for performance, DNS requests are cached at each level. So if you are at this host, an individual machine, there's maybe lots of these individual machines, of course, you will go to some local LAN level DNS server that might know where, for example, uwrf.edu is. Because if you visited in the past, then it'll cache that. And so the next time you need to access www.uwrf.edu, chances are some server will have it. And also that IP address, that DNS, it's called a record. It can time out after a certain amount of time. It'll say you'll just drop it. You won't have it in the cache anymore, because these network addresses do become what's called stale, or might not be in use anymore. And so if you don't find it here for whatever reason, that you haven't accessed it recently or you've never accessed it, then you go up to the next level and you ask there. And ultimately you might ask, if it's something that no one along this path has ever seen before, you might end up asking the root top level domain, or the root server, and the root will say, for example, if it's www.uwrf.edu, it'll say, I don't know where that is, but I'll ask the edu top level server. And then the edu will say, well, I don't really know where uwrf.edu is, but let me ask, wait a second, edu will know where uwrf.edu is, but it won't know where www.uwrf.edu is. And so it'll say, I know where uwrf.edu is, and so then you end up having to go to uwrf.edu, and then from there you will get the IP address for www.uwrf.edu. So that's how domain name service works. You might have to end up going all the way to the top, and then you descend down these levels. Everything is organized. The whole reason for this is it's not feasible to save all the different domain names in the world in one location. Plus they change all the time, and you can change it. If you have a web server, for example, you can change the IP address for your web server. And so for flexibility and and these things are really fast. You don't have to worry about the time that it takes to go from all the way from here. It just takes milliseconds to go all the way up here and then find uwrf.edu. So speed is definitely not a concern, although it may seem complicated right now. It works really well. Problem is there are some vulnerabilities in DNS services. So this is how it works. Let's say you are at this user IP address. You might ask, what is the IP address of some computer, like some webserver.com, like UWRF, www.uwrf.edu, and say, please reply to my IP address. That is the address over here. And then you will maybe send to your local area networks DNS server, or maybe if you're connected using an cable modem or DSL modem, you end up using your service provider's DNS server. And so these kinds of DNS servers along the way are non-authoritative for somewebserver.com. So that is, they don't really know what the IP address for these fully qualified domain names are, but they have a guess from past use. Let's say it went stale over here, then this primary DNS server might ask a root server, where can I find the IP address of this domain name? These root servers might say, I don't know, but .com should have the answer, and then that request gets sent to the .com server, top level domain server, with the question, what is the IP address of this something, somewebserver.com? .com, the servers at .com namespace will say, well, here is the primary DNS server of somewebserver.com, and so you should ask there. So this reply will go back to here, your primary DNS server, and then in turn this will ask, once it finds the somewebserver.com, the primary DNS server of that, what is the IP address of, for example, www.somewebserver.com, and then ultimately some DNS server will say, oh, here it is, I know, I'm the authoritative source for this IP address, and here it is. And then this answer will go all the way down to your browser running on your local machine, and then you have an IP address, and then from that point on you can use that IP address to connect to wherever that web server is. So effectively what all DNS does, although it seems pretty complicated, all it does is map domain names like, for example, google.com or www.uwrf.edu to those either IPv4 addresses or IPv6 addresses. This DNS domain name system is distributed. As you can see, there's a lot of servers involved, and so keeping all the names, the reason for this is keeping all the names in one table on one server is basically just not a good idea. And so you have authoritative name servers like this one responsible for just their domain, and this distributed structure is much more preferable. Okay, so next we'll take a look at the protocol that routes between smaller networks. So the internet consists of many what are called autonomous systems, or ASs. So for example, an ISP is responsible for all the subscribers in that service. Your cell phone service might coordinate all your data usage, and so they have their own autonomous system that's responsible for all the subscribers in that for that company. Same thing with cable modems and DSL modems, things like that. If you have one of those, then your service provider is responsible for managing that autonomous system. And so each of these autonomous systems control a range of addresses. So the way you communicate between these autonomous systems is through the use of the border gateway protocol, which is just a routing protocol that connects one autonomous system to another. And this BGP, or border gateway protocol, is really the core routing protocol of the internet. Once again, this is working at layer 3, but it typically also has some layer 4 functionality. So once again, all it's doing is it's figuring out where to send packets so that it gets eventually to its destination. So One of the famous cases where things went wrong is in from 10 years ago. In 2008, the Pakistani government ordered Pakistani ISP to reroute DNS requests to YouTube after a dispute about some content that was some videos that criticized the Islamic religion. And so, as a result, that ISP in Pakistan advertised a new DNS entry for this IP address 208.65.153.0, which was YouTube's address, YouTube's network. And so it was essentially pretending to be youtube.com. Through this border gateway protocol that we just talked about, this one misbehaving autonomous system was accepted unchecked by DNS servers higher up. So for example, in Hong Kong, a DNS server there picked up this change, and as a result, they ended up giving all requests for YouTube, or a significant number of requests for YouTube around the world, to this one ISP in Pakistan. This ISP was then clogged with requests, and it was total chaos. Nobody in the world could find youtube.com. There was no cat videos. I don't know how we survived this, but somehow we did. So how can we make things secure at the border gateway protocol? It turns out it is actually pretty vulnerable. It is getting better. It was vulnerable for a good long time, and BGP spoofing was used by spammers quite a bit. So for example, if you have an ISP A which is at this network address, remember 3.14.0/8, this is using CIDR notation, which means the network address is this part, the 8 bits, that's the first octet. Everything else is various network addresses or host addresses. And ISP B similarly might have a different network address, where 4.5 is the network ID part and everything else is the host part. So hope that makes sense. The /16 means 16 bits, and these are the 16 bits. So let's say ISP A and ISP B advertise their address spaces to each other, and the BGP routers update their routing tables to make sure that address or packets going to these two their routers know about. Now ISP E can advertise 50.50.0.0/16, which means this is the network part, this is the host part, and saying that basically any packet which starts out with 50/50 and then going to some host address in these locations should be sent to ISP E. And so it can advertise this subnet to ISPs A and B and ask them to advertise its space, and then A and B will then update their routing tables. Often it used to be without confirming authenticity, and that was the key problem. So that was the vulnerability. Didn't confirm authenticity. And so a lot of these security mistakes used to be handled by just local administrators for working for those ISPs. And they've made some honest mistakes. Some were probably maybe malicious, maybe, but mostly they were just, people were just trying to do their job and maybe made a mistake. That happens all the time. But spammers can take advantage of things like this. So the most widely used DNS software is Bind, or the Berkeley Internet Name Domain, which comes from University of California, Berkeley. This is pretty much standard on most Unix systems. The current version is 9, or current version 9 supports IPv6, so does version 10. Version 10 of Bind, that is Berkeley Internet Name Domain, is available on GitHub. As you can get the source code. It's called just called Bundy. So DNS started at a time when nobody expected it to be attacked or used for any bad purposes. What we were looking for, what we were looking out for, were hardware failures, not people purposely attacking this. So as a result, a hacker could gain control of a server running Bind and then use it to redirect network traffic if they really wanted to. And so once people realized that, they came out with this extension for DNS called DNSSEC or DNS security. They are in the current version of Bind and has been used ever since Windows 7, Windows 2008 server, and it is used by Google Public DNS has been used by Google Public DNS since 2013. So most machines, most computers these days will have DNSSEC, and there are all kinds of refinements and changes proposed for DNSSEC, including ones that involve things like blockchain. So that seems to be the way things are headed. So once again, BGP spoofing was used by spammers to to be able to send out their emails to wherever they want. Security issues used to be handled by admins, and in practice these ISPs swap or pay for routes with their peers, and so it's in their best interest to keep things working together, and despite all of this, there are some honest mistakes that do happen. DNS is actually even harder to manage than BGP, and it's very easy to be fed wrong information to drive clients to the incorrect site, and that's really the basic idea behind the cyber attack called pharming. So with pharming, that's with the PH, a villain redirects website traffic to a fake site using an evil or a poisoned DNS server. So it uses vulnerabilities in DNS server software. It can also be accomplished locally by modifying what's called a hosts file. So if you're on a Windows system, this is in system32/drivers/etc/host on a 32-bit system, or maybe even on a 64-bit Windows system too. Or if you look in /etc/hosts on a Unix system, and you can put in fake IP addresses. So a long time ago it used to be that all the names that you would ever use were in /etc/hosts. You didn't have domain name servers, but these days you have most of the time you have hardly anything in this file or in this file, and almost everything is sort of figured out for you by DNS servers. But if you put fake addresses, then you can sort of short circuit the actual DNS process. DNS cache poisoning is an attack where an attacker can feed fake DNS entries into some DNS resolver's cache. So I'm going to scroll back up to DNS. So you can put in fake IP addresses at any one of these levels, and thereby send clients to fake sites and divert traffic. You can also do what's called drive-by pharming, where what you can have is if you have an evil website with JavaScript code, and this code can do things like log in to your home router. So all you have to do is visit this web page, and as a result of visiting this web page, you will run the JavaScript code which will log in to your home router, assuming that you haven't changed the default password, which might be, for admin, default password might be admin, and that's the key to this attack working. Is there are a lot of people who just don't change their passwords, and so if you're one of those, they will try it. They will say, here's my admin username, password admin, and once it gets in, it'll modify settings on your cable modem router or DSL modem, and it'll make you use some fake DNS server, the evil DNS server, and so that after the client reboots, all future DNS requests from that client, from your computer, will be resolved by this, not by the real DNS server, but this evil one. And from that point on, the villain will be able to control all the web traffic. So for example, if you were trying to access a bank website, the client might be taken, that is your browser might be taken to a fake website with the same login page. You enter your login credentials, and then maybe it'll just say, oops, didn't work, or it might even redirect you to the actual website and things like that. As a result, the villain will get your credentials, your usernames and passwords, and store them for use later. So that's an example of drive-by pharming. All you do is visit a website and this JavaScript code executes on your machine, reprograms your router, and everything after that is compromised.